Welcome to Chapter 1 of the Composition-Based Features series. In this chapter, we'll learn the fundamentals of predicting material properties from chemical composition alone. Composition-based features, centered on MAGPIE descriptors, are classical yet powerful methods that convert chemical formulas into numerical vectors that machine learning models can process. By the end of this chapter, you'll achieve 3 levels of understanding. First, fundamental understanding, explaining composition-based features and statistical aggregation principles. Second, practical skills, using PyMatGen to parse formulas and MapMiner to generate features. Third, application abilities, applying these techniques to new material systems and integrating with machine learning workflows. In materials discovery, chemical composition is the most fundamental information. However, a string like Fe2O3 cannot be directly input to machine learning models. Composition-based features solve this by converting chemical formulas into numerical vectors. The process works in 4 steps. Extract elements and their ratios, look up elemental properties from periodic table databases, statistically aggregate these properties, and output a feature vector, typically over 100 dimensions for MAGPIE. There are 2 major approaches to describing materials. Composition-based requires only the chemical formula, produces around 150 dimensions, achieves good predictive performance, and can screen 1 million compounds in about 10 minutes. Structure-based methods like graph neural networks require atomic coordinates, produce thousands of dimensions, achieve higher accuracy, but are much slower. The choice depends on your application requirements. Composition-based features excel in 3 scenarios. First, discovering materials with unknown structures, where crystal structure is unknown before synthesis. Second, high-speed large-scale screening, where you need to predict formation energy for millions of compounds, achieving much faster speed than GNNs. Third, experimental data-driven approaches, where structural information is difficult to obtain from experiments. Composition-based features utilize elemental periodic table databases with 22 types of properties. These are grouped into categories: atomic structure properties like atomic number, period, and group, atomic size properties like atomic radius and ionic radius, electronic properties like ionization energy and electronegativity, and thermal properties like melting point and density. Each property has materials science significance. For compounds with multiple elements, properties are statistically aggregated using 6 representative statistics. Mean is the weighted average where weights are composition ratios. Variance measures the spread around the mean. Standard deviation is the square root of variance. Maximum and minimum capture the extreme values, and range is the difference between max and min. These statistics capture different aspects of the composition. Let's calculate atomic radius statistics for iron oxide, Fe2O3. Iron has a larger atomic radius with composition ratio 2/5. Oxygen has a smaller radius with ratio 3/5. The weighted mean combines these according to their ratios. We can also calculate the variance, maximum, minimum, and range. This process applies to all 22 elemental properties. Let's see how to use PyMatGen's composition class. First, import composition from pymatgen.core. Create a composition object with composition of Fe2O3. You can access elements, total number of atoms, molecular weight, and atomic fractions for each element. The fractional composition property gives the paradigm representation, and reduced composition gives the simplest integer ratio. Now let's explore how the periodic table connects to material properties. The periodic law states that elemental properties change periodically, and this periodicity directly contributes to predicting material properties. Understanding these trends helps us interpret why certain composition features are predictive. There are clear trends in elemental properties. As you move down a group, the number of electron shells increases, so atomic radius increases, ionization energy decreases, and metallic character increases. As you move across a period from left to right, valence electron count increases, electronegativity increases, and nonmetallic character increases. These trends explain many material behaviors. Different element groups have characteristic properties that determine their applications. Alkali metals like lithium, sodium, and potassium have low ionization energy and are used in batteries. Transition metals like iron, cobalt, and nickel have multiple oxidation states and are used in catalysts and magnetic materials. Halogens like fluorine and chlorine form ionic bonds and are used in perovskites. Rare earth elements have unique magnetic properties for permanent magnets. Elemental properties determine chemical bond types. Ionic bonding occurs when electronegativity difference is large, like in sodium chloride. Covalent bonding occurs when the difference is small, like in silicon-silicon bonds. Metallic bonding involves free electron sharing between metallic elements. These bond types directly affect material properties like hardness, conductivity, and band gap. In ionic crystals, coordination number is determined by the cation to anion radius ratio. Different ratio ranges correspond to tetrahedral, octahedral, and cubic coordination. For titanium dioxide, the ratio predicts octahedral structure, which matches experimental observations. This demonstrates how elemental properties connect to crystal structure. Mapminer makes feature generation easy. Import element property from mapminer.featurizers.composition. Create a featurizer with element property dot from preset with Magpie. Apply it to a data frame using featurized data frame. This generates over 100 features automatically. Feature names follow the pattern Magpie data statistic property name, like Magpie data mean atomic radius. Now let's look at real-world success cases where composition-based features achieved impressive results. These examples from major materials databases demonstrate that predicting properties without structural information can be highly effective for certain tasks. Formation energy prediction is the most successful application of composition-based features. Ward and colleagues in 2016 achieved excellent predictive performance on OQMD with hundreds of thousands of compounds using random forest. They demonstrated strong correlation on materials project data as well. Formation energy indicates compound stability. Negative values mean the compound forms spontaneously. Band gap prediction for semiconductor design also works with composition-based features. Ward achieved good accuracy in 2016. LMNet, a deep learning approach, improved this further in 2018. However, band gap has strong structure dependence, so GNN methods can achieve better accuracy when structure is available. Choose your method based on data availability and accuracy requirements. Thermoelectric materials that convert heat to electricity can also be predicted. Carriot and colleagues achieved reasonable predictive performance for ZT value prediction in half-Husler compounds. The most important features were mean atomic mass affecting thermal conductivity, variance of electronegativity affecting carrier mobility, and mean valence electron count affecting electron concentration. This shows interpretable connections between features and physical properties. The greatest advantage of composition-based features is computational speed. When screening millions of candidate compounds, this speed advantage becomes critical. Let's compare the performance between composition-based and structure-based approaches. The speed differences are dramatic. Feature generation takes milliseconds per compound for composition-based versus tenths of a second for GNN. That's about 100 times faster. Inference on 1 million compounds takes minutes versus hours, over 100 times faster. Training on 100,000 samples takes minutes versus an hour, over 10 times faster. This speed enables screening at scales impossible with structure-based methods. The optimal strategy combines both approaches. Start with 1 million candidate compounds and use composition-based filtering in minutes to narrow down to tens of thousands of promising candidates. Then apply GNN for precise prediction on this smaller set. Finally, select top candidates for experimental validation. This hybrid approach gives you both speed and accuracy. Composition-based features are essential when crystal structure is unknown. Pre-synthesis candidate compounds only have composition determined. Metastable phases from high-pressure synthesis or rapid quenching are hard to predict structurally. Amorphous materials like metallic glasses have no long-range order, so composition is the only descriptor available. In all these cases, composition-based prediction is usually the only practical option. For experimental researchers, composition is the most easily obtainable data. EDX or ICP-MS gives composition with high accuracy at low cost. Crystal structure from XRD requires more effort and Rietveld analysis. Precise atomic coordinates from single crystal XRD or neutron diffraction is difficult and expensive. Composition-based methods work with the data experimentalists naturally generate. Here's a typical experimental data-driven discovery workflow. Start by measuring composition experimentally. Generate composition-based features. Train a machine learning model on your data. Predict properties for new compositions. Experimentally validate the top predictions. If performance improves, optimize the composition further. If not, retrain the model with new data. This iterative cycle accelerates materials discovery. Before training models, analyze feature correlations to understand redundancy. Use pandas to calculate the correlation matrix and Seaborn to create a heat map visualization. Detect highly correlated pairs. These pairs indicate redundant features that could be removed for dimensionality reduction. Understanding correlations also helps interpret feature importance later. Let's see a complete machine learning workflow. Prepare your data with compounds and target properties. Generate MAGPIE features using element property. Split into training and test sets. Train a linear regression model and make predictions. Evaluate with MAE and R-squared. Create a prediction versus actual scatter plot to visualize model quality. This workflow generalizes to more sophisticated models. Let's summarize what we learned. First, principles of converting chemical composition to numerical vectors. Second, the 22 types of elemental properties from periodic table databases. Third, 6 statistical aggregation methods: mean, variance, standard deviation, max, min, and range. Fourth, implementation with PyMatGen and MapMiner. Fifth, success stories achieving strong predictive performance for formation energy. Sixth, the critical high-speed screening advantage. Before moving to Chapter 2, check your understanding with these questions. Can you explain composition-based features in 3 sentences? Can you manually calculate atomic radius statistics for Phi 203? Can you determine when to use composition-based versus GNN approaches? Can you generate a feature vector from a chemical formula using MapMiner? If you can answer yes to all, you're ready for Chapter 2. In Chapter 2, we'll dive deeper into MAGPIE descriptors. We'll explore the structure, 22 elemental properties times 6 to 7 statistical measures. We'll learn dimensionality reduction with PCA and TSNE for visualization. We'll analyze feature importance using random forest. Join us for a detailed understanding of the most widely used composition-based descriptor set.